Hey everybody, this video is on chapter 3.2 on logarithmic functions. So I'm going to try to do this quicker than I usually do. So I've written some notes for you that you can ready to go here. So we just finished chapter 3.1, which was talking about exponential functions. And exponential functions have this basic shape right here. That's if a is greater than 1, right? If a is less than 1 but still positive, then it would swoop down this way right here. But so that's an exponential function. Today we're going to look at logarithmic functions they are inverses of exponential functions. So if you remember back in chapter 2, I guess it was maybe chapter 1, I think it might have been chapter 1.8, we're talking about finding the inverse of a function. So if you remember, to find the inverse of a function, you switch the x and the y and solve for y. So if you have y equals a to the x, you would switch the x and the y. All right, the problem becomes, how do you solve for y when it's in the exponent? Well, that's where logarithms come in. So I'm not sure the history of the notation of logarithms and all that and how it works, but you just have to memorize that this right here is equivalent to this, right? So to solve for y, you now have a logarithm, which brings the y out of the exponent. All right, so log base a. So this is a base, right? This is called the base here, and this is the exponent. This is still the base, right? So I would say log base a of x is how I would word that. Right here you can see log base a of x. All right, so and remember, to find the inverse function from a graph, you just reflect across this line y equal x. Right, so if this is the exponential function, a reflection across this diagonal line y equal x gives you a logarithmic function. And we'll take a minute and just look at a couple examples here on Desmo. So if I have, let's do y equals 2 raised to the x. So here you have a exponential, and we'll graph the inverse here, which would be y equals log, let's see if it'll do a base for me. I can't remember how this works. Log, maybe not. Let me look at functions here. Probably should have researched this before I began. Here we go, there's log. Go back down there, log. Oh, there, that's the one I want, this one. So let me get rid of that and do this one. See the little a? So I want log base 2 of x, and there's the inverse. And then if you graph the y equals x, then you get the line of symmetry between these two functions. All right, if I try to make this up here like some fraction, let's say 0.5, I think we might have a problem. Because now if I try to change this base to 0.5, let's see what happens. That's not a base, is it? Hold on. Functions. Is it log base a at 0.5? Here we go, so it does work. All right. So, and you can see it's still symmetric about the line y equal x. All right, so now I'm going to just do some problems from the book, starting on page 216. We'll look at problem 2, and we have log base 3 of 81 is 4. And the directions say write the logarithmic equation in exponential form. So what we're going to do is we're going to change this to exponential form. And it's pretty simple. If you want to write the same expression in exponential form, this would be your base, this would be your exponent, and this is what it's equal to right here, 81. And you could, put that in your calculator and you would see that in fact, here, I got this, found this calculator I forgot I had on this old phone, which I like a lot. So if I do, let's do, now log base 3, we're not able to do it on this calculator. I'd have to do it a different way, but I can do this. 3 raised to the 4th power is 81. All right. Now, in Desmos, you can put in a base. Now, this old, I think that in the newer calculators, this is not, it's an old version of the TI-84 Plus. I don't think it has a log in it. Let me go to math and see if there's a log function. There might be. Oh, there it is, log base. Oh, yes, it does. Okay, so log base 3 of 81 is 4. All right, so you can see that they're related to each other, these two expressions. All right, so let's try another one like that. Let's look at problem 6, which is log base 16 of 8 is 3/4. So if I wanted to write that as an exponential equation, it would be 16 raised to the 3/4 power is equal to 8. All right, so this is just a skill that you need to have. It's pretty simple. Just practice a few. You have to be able to switch back and forth between these two types of expressions. Going the other way, I'll do problem 10. So now I'm given an exponential, 8 squared is 64, and we want to write that as a logarithmic function. So that'd be log base 8 of 64 is 2. Right? Log base 8 of 64 is 2. And let's see if I can make that happen. Where did I find that? I went to math and I went straight up to part A here. So log base 8 of 64 should be 2. And it is. All right, and that's it. Let's let me see if I can find one that's a little bit different. 14 log, nope, is 10 to the negative 3 equals 0.001. So that would become log base 10 of 0.001 equals negative 3. All right, and that's it. Okay, in the next section on the exercises on page 216, It says evaluate the function at the indicated value of x without using a calculator. All right, so for 20, we have f of x equals log base 16 of x, and x is 4. X equals 4. So what we want here then is f of 4, which is going to be log base 16 of 4. All right, so we can set this, we could change the form of this if it helps. We could switch it to an exponential from a log. So for instance, I could take log base 16 of 4 and set it equal to some other variable, whatever, we'll say y, and then I could, switch it to exponential to make it look different. So let's say you didn't have a calculator and you were confused by this. As it is, I could just put it in the calculator to get the answer. But you would have, what, 16 to the y is 4. So what power would 16 need to be raised to get 4? And the answer is 1/2, right? Because when you take the square root of 16, that's when you get 4. And if you remember, the square root, let me just write it over here. The square root of something is the same as the 1/2 power. All right, so y is going to have to be 1/2. Put that in. Hold on, my calculator's not treating me right. All right, so I'm just going to hit second enter, and I'm going to go back and change these numbers. So this is 16, and this is 4. So log base 16 of 4 is 0.5, which is 1/2. All right, so that's how you do exercises 19 through 26. Let me do one with a natural log. So if I have, let's say 24. 24 says g of x is equal to ln of x. And for 24, x is e to the negative 2. All right, whenever you see natural log, I'll just put this over here just to remind you, and I know you probably already have seen this, but just a reminder, natural log is the same thing as log base e of x. All right, so if I want to plug in for x, e to the negative 2, now I have natural log of e to the negative 2. And the answer should be negative 2. And the reason is because when the base of your, here, let me rewrite it. So instead of ln, I'll write it as log base e of e to the negative 2. It's kind of like as if these two things cancel out, right? That's just going to give me negative 2. But let's put it in our calculator and see what we get. So I'm going to do natural log of e raised to the negative 2. I should get negative 2. And I do. All right, some more things about logs. Let's see. There is a restriction on the domain. And I'm not seeing where that is. Well, I guess I'll just cover that later. Let's just continue with these example problems. All right, so that was number 24. So I'll do one more like that, 26. This is a continuation of that same set. G of x is equal to log base b of x, where x is equal to b to the negative 3. So very similar to what we just did. So if I do g and plug in b to the negative 3, that's just log base b of b to the negative 3. And since these are the same, the answer is just going to come out to be negative 3. It can be any number, right? These could be e's, like in the previous problem. They could be 2's, they could be 10's. If these are equal, then this is the resulting value of that function when you plug this in. All right, the next exercise says use a calculator to evaluate the function at the indicated value of x and round your results to 3 decimal places. All right, so for 28, so this is a new problem set. For problem 28, we have f of x equals log base 10. Now, whenever you have log base 10, you don't have to write the 10. If there is no number down here, it's assumed to be 10, which is called a common log, if you remember. And that's equal, x is equal to 12.5. And the directions say to use a calculator to evaluate this. So f of 12.5 equals log of 12.5. Notice I did not write the 10 because I don't need to. That on your calculator is right there, log of 12.5. And I get approximately 1.1. Right? It's approximately 1.1 because you're going to have to round that. If you try to round it to the 9, it's just going to round up to a 10. So about 1.1. To 2 decimal places would be 1.10. All right, so that's it. That's all you're doing is you're plugging these, getting used to your calculator functions and plugging them in to get an answer. So 30 f of x equals 3 times natural log of x, and x is 3.32. So if I'm going to do f of 0.32, sorry, 0.32. I get 3 times the natural log of 0.32. So 3 natural log of 0.32 is approximately negative 3.42. All right. Easy peasy. So that's how you work that next problem set. All right. When you get to the problem 33, you have graphs. It says use the graph of y equals log base 3 of x to match the given function with its graph. So I'm going to skip that part for now. Okay, I'm going to skip problems 33 through 38. I think you guys can figure that out on your own and skip down to problem 40. So 40 says find the domain. So I need the domain. X-intercept. in vertical asymptotes of the logarithmic function and sketch its graph. So I also need a graph. All right. So looking at problem 40, we have g of x is equal to log base 6 of x. Okay. All right, so let's just graph this on Desmos. So I want log base 6 of x. I don't need all these parentheses now, do I? Get rid of that. All right, so here's the graph. So you can see pretty clearly that there is an asymptote right here, and it's y equals 0. Remember, this is the I think this would be the inverse of y equals 6 raised to the x, right? So 6 raised to the x. Raised to the x. All right. So as you can see, this y equals 6 to the x is exponential. And you can see that the x-axis is an asymptote, right? So if you take the inverse, then if the x-axis is an asymptote, then the inverse, which is the logarithm, is the y-axis is going to be an asymptote. Here you see that it has a y-intercept of 1, but the logarithm has an x-intercept of 1. So, you know, the x and the y's are just switching between the two. So to answer these questions, it says, what's the domain? You can clearly see that the domain is basically all x's greater than 0, right? So the domain is all x's such that x is greater than 0. There's different ways to write that, but that's one way. So we got the domain. The x-intercept, that's we said was 1, isn't it? Right there. So the intercept is x equal 1. Right? So how do you make y 0? By letting x equal 1. Okay. What's next? Vertical asymptote. Vertical asymptote is the y-axis. Right? So vertical asymptote is the y-axis, which is x equals 0. That's the equation for the y-axis. And then the graph is right here. So you would just, you know, sketch a graph as best you can. It looks something like this. Comes up, crosses through right here at 1. And the range should be all values because it goes down forever, and I believe it does also increase without bound, although it seems to be reaching a max, but it should keep going, right? Because as x gets bigger, y should get bigger. So why don't we look at another problem in that same set. So that was number what? That was number 40. So now we'll look at 44. Y equals log base 5 of x minus 1 plus 4. Alright, so you can see here that you're subtracting 1 from x, so that's going to be a shift to the right. And then you're adding fourths, so that's going to be a shift up. So normally all these should I think all of these should cross the x-axis at 1. So let's see, if I change that to a 5, you can see that it still crosses the x-axis at 1, right? But when you take away 1, that's going to shift it to the right 1. So now it should cross at 2, right? So if I put in y equals, hold on. It's the bane of my existence right there. All right, so functions log base A. Doggone it. I wonder if I can cut and paste this. Can I drag it down? No. Nah, forget it. So 5. So now I'm going to put in x minus 1, and my prediction is it'll shift this graph over to here. Right? And then when I do the next bit, which is to add the 4, what's that going to do to the graph? I should bump the green graph up 4, right? So plus 4. So it went up from here 1, 2, 3, 4. Now it goes to the coordinate 2, 4 right there. Okay. So what's the domain? Well, if you notice, we now have an asymptote. Let's see. Is the asymptotes should be 1, right? Because it was 0, but the whole thing got shifted over 1. So now we have an asymptote at 1. So the domain, therefore, is all x's such that x is greater than 1. So it can't be 1. Why can't it be 1? Because if you make it 1, you're going to take the log of a 0, and that just doesn't work. You can't take... Hold on, I'll show you on the calculator. If I do log of 0, I get an error domain. Oops, you can't see that. Hold on. There you go. So if I do log of 0, I get error domain. So in a logarithm, the argument, which in this case is x, has to be greater than 0. Has to be positive, right? So this is a no-no right here. But whenever you do like x take away 1, as we do here, right? Now it's 1 that makes it 0, right? So 1 minus 1 is 0. So 1, x has to be bigger than 1 in this case. All right. What about, what was the next question I have to answer? There's the domain. the x-intercept. Well, the x-intercept is still 1, isn't it? Looks like it's, no, it's slightly more than 1. It's, hold on, let me turn this one off. 1.0016, so it's bigger than 1. Obviously, it has to be. So x is equal to 1.0016. All right, so that's the x-intercept. Now, one way we could find that by hand is just make y 0. So I could do log base 5 of x minus 1 plus 4 equals 0, and then start working on this log base 5 of x minus 1 equals negative 4. Now I could change this to an exponential. I could do 5 to the negative 4 power is x minus 1. And 5 to the negative 4 power is there's where you get the 0.0016. Now add 1, and you get 1.0016 is x. Right? So what did I do? I just set the y value equal to 0 to get the x-intercept. And then I worked it out to here, and then I changed it to an exponential, and then found the value of that, and then bam, you're done. So you get the x-intercept. Okay, the next thing we have to find is the vertical asymptote. And as we already saw, well, that got shifted to the right, so it's x equal 1. And we also have to sketch a graph. So here's 1, and there's an asymptote here at 1, right? So it comes up, and I know it goes through what was it? It was 2, 4, I believe, right? Yeah, 2, 4. So if I go over here 2 and go up 1, 2, 3, 4, I know the graph's going to go through there, so it's going to skim along here. It crosses almost at 1, and then it does this kind of thing right here. This is 2, 4. All right. And that's about it. And then I guess in the next lesson what I'll do is I'll do some applications of logarithms. And we'll talk more about the domain and range of logarithms and all that. So thanks so much for watching. God bless you guys. Have a great day.